Brazil team. Today I'm present to the problem 13, light bulb. The problem asks you the ratio between thermal energy and light energy emitted from the small electric bulb depending on the voltage applied to it. So, first, the introduction. You first introduce our definitions, some theory, some the electric bulb construction, and then make some tests, analysis, and our conclusion. First, we'll talk about the energy types. You have the electrical energy, that will be the current that will pass through the lamp. You have the thermal energy, and the light energy that will focus on the bulb. The energy conserved. So you have that one type of energy you cannot be destroyed or created. It will turn in another type of energy. That's known as energy conservation. And you have the energy transport that can be given by conduction, convection, or radiation. Another definition is the Joule law. Joule law is when you pass a correct current, electric current through a resistor, and the electrons moving collide with the particles of the material. So the collision raises the atom's vibration and raises the temperature. So it's known as Joule law. And another important thing is the black body. Black body is a idealized physical body. That's not exist a real black body. But some objects have very similar behavior. Black body has perfect absorption and perfect emission. So all incident energy will be absorbed and emitted, and when you make the temperature rise, and it will be emitted by the black body. So it will be emitted as a radiation. As you increase the temperature, the frequency will rise too. So the bigger the temperature, bigger will be the frequency, and it can reach visible wavelength frequency. You have another important figure is thermodynamic laws. Here we have the Stefan Boltzmann law. Is very famous. It gave the total energy, total irradiance of the material. You said in the Wien's displacement law, it talks about the distribution of the wavelength. But all these laws are just particular case of the Planck's law. Planck's law is, as you can see some expressions of the Planck's law in the graph of it. It describes all radiation emitted by a black body. So finally you have the bulb. The bulb is composed by the glass, the tungsten filament, low pressure net gas, contact wire to the tungsten filament, and electric contact. And how the bulb works. The electric current passing through the wire, you cause the Joule effect, and you make lots and lots of thermal energy, make electronic excitations, generating radiation, including visible radiation. It is very visible in the video. So you have a lamp. So you first and you receive a power, energy power. There will be dispersion in conduction, irradiation, loss in the system, the tungsten filament, and convection in the gas. But there's not this. Okay, but the gas is low pressure and it's inert, so the current will negligible, and the loss in the system and pollution is negligible too. And they have a part absorbed by the glass, but is the negligible too, because the glass is so small and the glass have high transparency. It's transparent. And as the energy absorbed by the glass will make convection and irradiation, as the energy comes from the energy absorbed by the glass, it will be negligible too. So you focus in this filament here. So this filament will produce radiation, infrared, visible, and ultraviolet. Is the most part of energy will come from here. So we consider infrared energy thermal energy, ultraviolet 2. But visible wavelength have similar characters. So we consider all the radiation as thermal energy, and the visible light will be considered as light energy. So that's our limitation for the problem. First, we have to know if the lamp the bulb is black body. With this expression, you see that potence, the power, and the power of the lamp and the black body behave. And here the resistor behave. And developing, you see that if you have this, if this expression is constant, you have that the body will behave like a black body. So it's a small like bulb, variable source of energy capacitor connector in multimeters. You have the values, and in a graph you see that this relation is too close, it's almost constant. So we consider the lamp as a black body. So we use a small light bulb diffraction grid, a light dependent resistor, have a connectors, multimeter, and a voltage source. We slap the LDR over the circle, and you know that wavelength is proportional to the sin of theta, and the conductance is proportional to the luminous intensity. Our results, but you really can see the results when you put it on a graphic. You see that is very, very, very similar to the Planck's law. So you really can apply the Planck's law. So what you make? You developing the resistor equation here. We see that this relation can be used. So we can know the resistivity of the lamp at any temperature. And as you know, the resistivity of the tungsten, we know by the literature, and the resistance, and you measure the resistance of our lamp, 0.2 ohms. You can find the temperature by this graphic of the resistance of tungsten by the temperature. So here you have the temperature of the bulb, and with the temperature you can find here a graphic. We can find the duration, because here's the thermal energy of emitted radiation, and here's the visible radiation that the defined target of the Planck's law by the visible wavelength. So here you can see that depends on the area of the filament. It's very hard to calculate, but when we make the division, the area cancelates. So you have the proportion. You can find the proportion. So here you have our results. As you say that the bulb only behaves as a black body when he's 5 or when he's submitted at 5 volts or more. You only check the results for 5 or more volts. Here you have our results, and you see that the max you are rating by the voltage. You see that our max ratio is 3.25. It's a graphic. You see that really. So the conclusion is that the light bulb behaves as a black body, in fact. So the Planck's law can be used, and the temperature can be measured by the resistor equations. And finally, the light bulb will present very low ratios of the light energy divided by the thermal energy. So that's all.
Let's begin with some specified questions.
We don't have the first one. I think that the first one.
Speak
What?
up so that we can hear, please.
Have you considered the parameter emissivity of tungsten? The coefficient of
Yes.
emissivity?
It's
So,
almost one.
almost one. Okay. And which lamp, which light bulb did you use? What are rated characteristics? What are characteristics of your bulb?
It's very small, and it's
So it's for a pocket torch.
huh?
For a
No,
pocket bulb.
it's specific for the experiment with the LGR, as that I showed.
Have you gotten any photos
Huh? Okay.
of the bulb you used in your experiments?
No, I have in short plots.
Well then, I guess a few more questions. Have you considered, did you perform any experiments to prove that heat conductivity factor and as well as convection are negligible?
Yes, the first experiment showed that because it's black body and all the energy is the radiation because it's almost constant in black body, so it's negligible.
Well, and once again, in your experiment, you have measured light energy
Yes.
with
No, I
yes,
proportion.
I got it. So, and you use no equipment to measure light to investigate some light properties.
yes. I for example, we don't put in the
So you have only used Planck's law.
what?
You use Planck's law.
Well, yes. I use it. I LGR. It,
And have you tried to measure the temperature of filament
I
during your experiment?
made sure the temperature. You can see this.
I
Slide.
mean the direct,
Okay.
not formula.
can-
Not formula.
No,
but
you can't measure it direct. For example, a thermometer is indirect, so it's very efficient way to measure it. Temperature.
Excuse me, your time is delayed for questions.
So it's
2 minutes.
Okay. So now it's 2 minutes and it's finished now.
Yes.
Okay.
And you prepare for
Can I take it off?
Гениальный показатель, а потом еще опять не разбавляешь. Я докажу, что пусть мы можем если Паша просто скажет, что можно сдавать, не проводишь,
Let me represent myself once more. I'm a member of the team of Russia, and now I will be I'll act as opponent to problems to solution of the problem number 13, light bulb. Well, let's briefly overview the main advantages and disadvantages of the report. Well, as for the advantages, some positive side. This sequential research was performed by the reporter, but however, I can but mention that there weren't enough specifiers in his presentation, and as we saw from his answers, well, it's not detailed enough. Well, then the next point, he investigated the theory, and doubtless that's an advantage. But he investigated the theory, and he used only the theory to get his results. Well, what I really mean is that he didn't use any equipment to measure the light energy. Maybe not energy, but somehow to measure energy and to measure maybe temperature, maybe luminosity, maybe, well, there are many ways of that. I'd like to leave that point for discussion. And he used the theory to get his electrostatic electric results to the light energy using lamps. Well, let's proceed to the negative sides. Well, we absolutely disagree with the statement that heat is only caused by emission, by radiation. Other parameters cannot be negligible, and I would like to discuss it further. Well, the next point is that some of your graphs, well, it's a little bit hard to read them and to understand. So maybe I would like to come back to some of them. Well, definitely it was lack of experimental photos, and as the cause of that, as the reason of that, it was inappropriate experiment itself. It wasn't enough for to solve the problem correctly. Well, I think the most important negative point is the Planck's law approximation. It's perfectly known, and it's written in all the scientific books and many articles that emissivity of tungsten is not equal to 1. Thus, Planck's law cannot be used in the way you did it. There are several ways. I would like to discuss it with you later. Well, and the emissivity is also a function of temperature and wavelength. There was nothing said about it. Well, a little bit. It was a little bit hard to understand the tables because they were really fastly shown, and it wasn't easy to concentrate on them. And I think we'll proceed to discussion points. So those are the details of your experiment, what you have done, then an approximation of Planck's law in your research, then measurements, then direct measurements instead of just you using the theory, and Planck's law. Thanks. I would like to proceed with discussion. Okay, I guess it's your turn.
No problem.
Берешь в конце речь. Ты помочь мне? Ну, помочь.
Well, the first stuff that they have just remind me, let's switch to the one of the first slides with formulas. Maybe the 8th page attempts. It was a strange coefficient. The previous here, the 13th, yeah.
Okay.
The strange coefficient. I mean K. Could you please
I can explain the equation. This is the power equation of Dylan. Okay.
Sure.
Okay. So this is the black body behavior.
Well,
Okay.
yeah, that's only for black body. So.
Okay. Okay. This experiment is they show that the lamp is a black body. Okay. So if I develop the equation, I come to this result. Okay.
Yeah, that's
Okay.
absolutely.
This is the resistor equation, right? It's
So-
proportional to the temperature, right?
Yeah, it is like one question. It's only theoretical, yeah? Have you checked it with
Okay.
experiment?
It's theoretical and it's observed in the practical results.
So you observed right the direct dependence. Okay.
It's some, okay. It's one thing that's very basic in the literature. So I guess maybe I would prove this equation of that, but I have the time for the presentation. So that's a basic equation. So I can not.
Yeah, those are
Okay, so I developed it as the resistor equation and found that the temperatures is proportional to that. Okay, when I
So you
make a union of the
just
two
put
equations.
it here, yeah.
Yes, and found that this this result and found the result. This is a constant value, okay? This is
So
constant,
that's the
okay?
constant which
And
shows,
okay.
as I can see, the area, the coefficients, and constant, and what's C, and what's C here.
Okay, is a constant.
Constant of what does it mean?
Okay, it's proportional, right?
Right,
This.
right
Okay,
here.
so
Here
that's a
I
constant,
get it, yeah.
right?
Yeah. So there's a constant, and what about the value of that constant? Have you got the
It's
value?
not necessary to measure, okay? Because our constant is that constant, okay?
So I got them.
Okay.
Let's
Okay,
proceed.
so you agree that if this expression is constant, that will behave like a variable, like what? So, right?
Absolutely. Well,
Okay.
a black body, okay, but what
So-
about the tungsten itself?
Okay, the black body that I'm talking about is the tungsten filament. If it behaves like that, it will be a black body.
A question: where did you get the information about the?
With my experiment, did you see?
The-
It's
no,
almost
I'm
aligned.
sorry, no. Where from did you get the information about the emissivity of black body? We have definite.
Okay, one thing is, I must let very clear. I didn't say that the black body emissivity is 1. I said it's very closely 1.
It's
So
close
the
to one, so it's maybe say 0.9, 0.9.
yes, almost that.
And
So
I'm
the
still
difference
disagree.
must not be considered. So because it show here that it's almost
Sure, but it's much more different from the.
okay. That I show you this equation, right? You agree that if this equation is constant, that
No.
will be related,
Let-
okay, like
yeah.
black body. Okay.
Let me
You-
state myself.
Okay.
I agree to your black body equations, but the main point I don't agree with is the equality of black body and tungsten. So.
Okay, but this is
okay.
tungsten, right? So
And
this is
what is shown here and here? What about the axis? What is shown here?
okay. This is the potential difference here. So
So,
I show that
So horizontal is potential difference.
okay, yes.
Okay.
And here is the
The ratio.
is this
No.
is this value here.
This value.
Okay.
Well, this wasn't.
I showed that it's constant, almost constant, so that behave like a black body.
So, but how does it accord with your previous formula? As I can see, it's almost almost aligned only with higher voltage. And what about the lower?
Okay.
It doesn't seem it's a little bit.
When we have okay, or in a lower voltage, the lamp can almost not emit light. So we don't consider it because the problem is
So you just
lamp
don't-
emitting light. So if here you cannot even emit light, you will not consider it in this case.
Well,
In the initial behavior of the bulb, it's not like what.
thanks a lot.
Okay.
Well, did you consider the derivation of just one minute for
Okay.
have you tried to derive the required ratio using a Planck's law from the very beginning? So I mean to define the well, at first you can define the area of tungsten, and then
I don't
this.
think
Well, maybe you go to one of the previous slides. I'm talking about quantity, the special density of red intermittence. It's different here. So no, oh yeah, here. I mean the intensity. So, do you think if you could not measure but derive this intensity, knowing some properties of the bulb, knowing the temperature and the wavelength? do you think it's possible?
Derivation, make a derivation?
Yeah.
Yes.
From that. However, this wasn't performed by you. By the way,
Okay.
what's the wavelength for visible light?
It's 400 to 400 to 700 nanometers wavelength.
Maybe not 700 to 8, but okay.
Okay, it's okay. The light will vary from person to person. So this
Absolutely.
is the generic value. So you have to take
yeah.
take some value. So you take this generate.
And what about the whole area under the Planck's curve? What does it mean? How do you think the whole?
Okay. The area.
Not lines. I mean the area. Well, let's consider this line.
Okay.
What
you are
about
saying
the area?
Okay.
This whole space. What's that?
the area? This area?
Yeah.
Okay.
What do you think?
The area of all.
I mean the area of this figure.
Okay.
What
The
is
area
it?
of the figure you represent all the emit
All the
all
emitters.
the emitted
Emitters.
yes.
Yeah. So, and do you think it's possible to calculate the area of this figure?
Yes, I did it. I can show
Yes,
again.
please.
I did it here. This is how I calculate the ratio of the. It's here.
It's here. So,
It's the Planck law, right? Here's the definite value. The definite
so
value.
here's
This
the area.
Yeah. No.
I mean A is the area.
No, it's the area of the tungsten
Of the
filament.
tungsten, yeah.
Here's the area of the graphic integer. Okay?
Absolutely, yeah. That's
Here is the integer of all the
all the energy.
that's the Stefan laws. That thing, the Stefan laws is the integer of the Planck's law for all wavelengths. It's more simple, so I put
I
the
agree with
Stefan
you.
law.
And once more, I can see here one. I think the quite big mistake because there are definite there is the definite information that there is also an emissivity here to be considered, and besides it changes. It's a function. It changes depending on the temperature, and temperature has to change, right? As the voltage grows.
Can you repeat this?
Well, when the voltage grows,
Okay.
when the voltage grows,
Okay.
okay, what happens to the temperature?
They increase. I show you.
Yeah, it
I make a graph.
yeah, of course. You used the graph from this. Okay.
Here's the graph. Oh no.
Potential difference.
Yes. It's the potential difference and here's the temperature. I measured.
So, and you consider only potential difference, and you don't consider the change of currents.
What?
Because, well, look at the when temperature changes, the resistivity changes.
Yes.
Do you agree? And when resistivity changes, the current force has to change.
I use this fact to calculate the temperature. I calculate the temperature by the changing of the resistivity. Okay.
I'm sorry, by changing, you change it manually. How did you?
Okay. The resistive will change with the temperature. So I use it to calculate the temperature of the bulb.
Thank you from the reporter and opponent. Questions after the report, reviewer, after the reporter and opponent. 3 minutes.
Юля, будет там еще что-то?
Okay, good afternoon, respected jurors, members of the opponent teams and the audience. At first, I have some questions to the reporter and the opponent. At first, I want to ask about transmissivity of the glass. Do you think should it be taken into account?
It shouldn't be taken as a point.
And opponent, what do you think about it? About transmissivity
About
of the glass?
transmissivity, well, it's definite that it's So there are only ultraviolet lights which are transmit, and it's not important here because ultraviolet doesn't bring much energy. It's negligent.
I understand. And another question to the opponent about emissivity of tungsten filament. Do you think that it is really very important?
Yes, definitely. It's really important because here is the main idea in the theory of this problem is Planck's law.
And reporter, do you agree with your opponent about emissivity of tungsten?
Yeah, I agree, but I believe that's almost one. It's
Okay.
important. It's almost in
You
almost.
showed us values of the ratio of our light bulb between two energies. And what about it is experimental data or theoretical data?
It's experimental because I got these experimental results and using it to calculate the ratio. So experimental.
Okay, and have you tried to estimate this ratio theoretically?
Okay. Yes, because the theoretical view depends on the temperature. So I used it with the temperature that I got.
And what about accuracy of your measurements? There were no errors shown in your presentation. You told us about experiment. What is the error of your maximal ratio?
Can you repeat? I don't get it.
About accuracy of your measurements. What is the error of your measurements?
Okay, I use a multimeter, so I got a highly precise results because I measure the resistivity with the voltage and the current. So I got a multimeter, so I got a highly precise.
And I have another question to the opponent about radiation of gas and light. About radiation. Yeah. Heated gases and light radiate. How do you think? Is it influence on the phenomenon?
Yeah, of course it has the influence on the phenomenon, but it may be accounted by considering the whole energy, and it equals the product of the voltage and currents.
Okay, I understand. Now I'll prepare my presentation.
There's something with the wire.
projector, maybe I make review from my laptop.
Yes.
Okay? If it is okay, I'll make it.
Технические проблемы не связаны с ним. Да, три. Какие еще связаны с нами? Там, где шел такой.
Okay, some problems. So, good afternoon, respected jurors, dear opponent, reporter, opponent. My name is Julia Sapronova. I'm representative of Belarusian team, and now I'm going to make review for the problem light bulb. At first, let's speak about report. At first, we saw the energy distribution on what is energy spent on, and reporter told us that it is spent on emission and heat losses such as convection and thermal conductivity. That was really good that he made this scheme for energy distribution. The reporter used Planck's law for description of emission. I think that it is really good because Planck's law really can be used for emission of anybody. Reporter showed us the determination of thermal and light energy, and I fully agree with him that exactly these energies should be taken, like light energy and thermal energy. Then he didn't take into account the radiation of gases. I think it takes little influence into this phenomenon. And of course, the main problem was to find the ratio between light energy and thermal energy, and reporter do this. But he used approximation that lamp is really is black body. I don't agree with him. He didn't show us experimental measurements of light energy that mentioned opponent, and I think that was really not good. And there was no comparison between theory and experiment. And there was no errors shown in this problem. And about discussion. At first, opponent told us about emissivity of tungsten. I really agree with him that emissivity of tungsten should be taken into account because our light bulb is not black bodied. Then he speak about measurements, about some accuracy, about some measurement instruments that he used. Also, opponent told us about Planck's law, about using of it, and of course, I think was of course he asked about some parameters that was taken into account in this theory, and he also asked about the range of visible spectrum of light. I think it is very important because of it is taken in the theory in range of integration of things. And also he asked about plots and tables because not every table was clearly understandable, and I think it was really good. And then about matrices. Opponent told us about meaning of thermal energy, and I don't think that any other energies should be taken into account because we don't consider losses, because losses is not emission of tungsten. Then he told us that Planck's law can't be used as approximation of emissivity, but I agree with the reporter that it really can be used, but emissivity and transmissivity of glass should be taken into account. And opponent pay too much attention to one equation. Thank you for your attention.
Thank you. The final results and conclusions reported. You have 2 minutes.
Okay. I won't say that. I don't say that blood is a black body. I say that's it's really close to a black body. And I don't say it because I read somewhere. It's because I show it experimentally. This is a experimentally Olympiad. So I show it experimentally. We make experimental an experiment, and you show that it can be considered, it can be approximated to a black body, and it's you take the most, you think you take the most relevant parameters, and because of this, our ratios make sense, and that it will be correct, and you measure the filament temperature. As you can see, with this measure with the resistivity of the tungsten, the variation, use the variation of the resistivity to take the temperature. It's used by for that. So because of that, we can find the temperature and found the ratio. And found the ratio use both experimental and theoretical physicals. Because of that, we find that's correct. And okay. And finally, about the errors in the experiment. The experiments have the errors in the multimeter. It has some errors, but it's really small. It's, especially because the temperature measure was really high. And about direct measurement of the light, we use the LDR to make this measurement, direct measurement. Okay, thank you.
I'd like to ask the reporter, you said that the temperature and the resistance are linearly dependent. How do you know this? Do you measure it, or do you find it somewhere, or what is?
I can use you can write. It's you know, okay, you know that because the okay, because resistance, the resistivity, okay, varies with the temperature. So if it's proportional, the resistance will be proportional too. Okay.
So it is based on this equation.
Yes.
And are you
So
sure that
the
is
okay.
it valid for the whole range of temperatures that you are using?
Okay. It's not a linear, but you can approximate it. It's almost linear variation of the temperature. It's really close. Okay.
So I have one more question. How did you measure the temperature of the filament? Is that by this?
We measured with the
You measured resistance?
resistivity, and the resistance is equal to resistive times the length. So, okay, so I have that. I consider this constant because it varies almost really low or varies. So if this is constant, if I have the resistivity at present at 300 Kelvin and resistive at 300 Kelvin, and I measure the resistance at any temperature, I can find the resistivity at that temperature. So I can use it in the graphic of the resistivity of the tungsten with the temperature, and I found the temperature. I use it to find the temperature of the filament. The graphic is easily found in the literature. The graphic of the resistivity of the tungsten with the temperature. You can find in the literature.
With which accuracy can say that the light bulb is a black body? I mean, you didn't compare the results with, sorry, it's called equations, quantity, quantity.
Okay. The tungsten filament isn't a black body. It's closed. I can say it's almost what is it? I don't know exactly the difference between, but I can say it's very close, and it can be considered a black body. It's very clear in the graph. It's very clear.
So it's qualitative, not quantitative. You didn't compute theoretically
Can
the
you talk
results.
a little louder?
I mean, you showed that the figures are the same, but quantitatively.
No, I make two experiments to show that. I use the LGR, and I use it to compare the potential difference in the voltage. I found a relation, and I prove it that if it's constant, that will be the black body behavior. And I make a graph and show that the results are almost constant. So I have a quantitatively that it's really a black body. I don't know if it's possible to see here the graphic. I focus the part that really shows that's constant. So because of that, I can say that's really a black body. Thanks.
Do you want to see?
Thank you.
Do you want to see? Yes. I found, oh, okay.
Наводи, смотри, сколько ставит. Сейчас сумма мила.
Ты упомнил, что так можно робить?
Можно. Они все равно потом подотчетны. Они все равно потом подотчетны.
Ну, я разумею, але ведаеш, гэта можа быць непрыемна.
Закрой блик.